A quantum internet fundamentally enhances the internet technology that we have today. It enables us to send quantum bits, qubits, from one point on the internet to another. So a quantum internet has many applications that are impossible on the internet today. It can make many things more efficient, and in fact, to use a quantum internet, you also don't need to have a large quantum computer at home. So probably the most famous application of a quantum internet is to use it for secure communication. So secure communication means that I am going to send data to you, like my credit card information, or maybe state secrets, and I want that no one is able to listen into this communication. A quantum internet allows us to use quantum key distribution that enables secure communication whose security relies only on the laws of quantum mechanics. In particular, it's secure even if some eavesdropper who's trying to snoop into our communication has a quantum computer. And it remains secure even if this eavesdropper buys a quantum computer tomorrow. But a quantum internet has many other, possibly less well-known applications. Using a quantum internet, we can use a quantum computer in the cloud. Quantum computers are pretty expensive. But of course, we want to use this computing power. So the first quantum computers are likely going to be somewhere in the cloud. Now maybe I want to use this quantum computer to perform a simulation on some proprietary material or a new medicine, or possibly even my own DNA. So I don't want to give my DNA to this quantum computer. So it turns out that using a quantum internet, we can use this remote quantum computer in the cloud securely in the sense that it has no idea what we're going to use it for. Quantum internet can also do all kinds of other cool things. Like it's good at synchronizing clocks much more accurately than we can do classically. It can be used to enhance password identification to some server far away. And curiously, we can even use it to play better at an online game.
Roughly, there are two kinds of quantum networks. Unentangled networks, which are good primarily for quantum key distribution across a network where the secrecy of those bits is guaranteed via the underlying physics rather than some sort of mathematical function. And these networks exist. They are limited in distance and they're single purpose, but they do exist. At the other end of the spectrum lie entangled networks, good for many different purposes, connecting quantum computers into a real quantum internet. And these things are particularly difficult to build. And in order to understand quantum networks, the single most important concept you have to understand is entanglement. So if we have two quantum systems, one on the left and one on the right, and they are in some sort of entangled state, what that means is that their behavior is shared in some fashion and they are not completely independent. If you measure the one on the left to figure out what it looks like, what it's actually doing, you will find that it's either pointed up or pointed down, and in this case it was pointed down. At the same time, you will learn what the one at the far end is, even if these two systems were far apart. This is sort of the basic idea of entanglement.
So what is this quantum internet? So on the surface, it looks a lot like a classical internet. There's computers, and we're going to send data from one computer to another. Only on the quantum internet, this is a quantum computer, and I'm sending quantum data, qubits, from one place to another. So these qubits are pretty special. For example, we cannot copy a qubit. Unlike a classical bit that can be either 0 or 1, a qubit can be both 0 and 1 at the same time. So what is it about these qubits that it enables all these applications? 2 qubits can be entangled using a quantum internet. But there's actually only 2 features of quantum entanglement that lie at the bottom of all of these applications. So what are these 2 features? So the first one is called maximum coordination. Let's say I've used the quantum internet to entangle a qubit here in Vienna with some qubit far away, somewhere down in Sydney. And I'm going to perform a measurement on my qubit. And let's imagine a friend down in Sydney performs exactly the same measurement. Now, if we make the same measurement, we will get the same measurement outcome instantaneously. You can think of a measurement as asking a question to a qubit. I can ask, qubit, are you pointing left or are you pointing right? And if I ask the question to my qubit here in Vienna and my friend asks the same question down in Sydney, then if I see left, he will see left, and if I see right, he will see right. And this happens instantaneously, even though the answer is not determined ahead of time. And the cool thing is that it actually works for any question that we might have asked to this qubit. If I had asked, are you red or green? We would have seen exactly the same. We get always the same answer. So entanglement is maximally coordinated. And it is this feature that makes it naturally so suited for tasks that require coordination or synchronization. So what is this second feature? The second feature of quantum entanglement is that it's inherently private. If I have 2 qubits and they're completely entangled with each other, then it's physically impossible for any other qubit or actually anything else in the universe to have any share of this entanglement. This means that if I have a qubit that is completely entangled with your qubit, no one else can have a share of the entanglement. Our 2 entangled qubits form a private connection that no one else can share. So entanglement cannot be shared, and it's inherently private, and it's this feature that makes it naturally very suited for secure communication. But given that quantum entanglement is so cool, you might ask, why don't we have a quantum internet yet? It turns out that we can actually send qubits over short distances. You can go online and actually buy a commercially available box that performs quantum key distribution, quantum secure communication, over standard telecom fiber over distances of roughly 100 kilometers. So the real challenge in building a quantum internet is to get these qubits to travel further than these 100 kilometers. Why is it so difficult for these qubits to traverse long distances? If I want to send a qubit down a communication line, we are sending a single photon, one particle of light. So you can imagine that if I take one single particle of light and I send it down a communication line, very soon it will be lost. Remember that also qubits cannot be copied. So if it's lost, it's gone. I cannot resend and try again. So how can we hope to send these qubits over long distances? So fortunately, as I mentioned, we can actually send them over short distances. So let's put like a box in the middle, and the box is not so far away from the left, and it's not so far away from the right, namely close enough that I can send qubits both from the left and from the right to the box. What we're going to do is we're going to take 2 entangled qubits on the left, and I'm going to send one of them to the box. Box is not far away, so we can do that. I'm going to take another 2 qubits, which are entangled. I'm going to send one of them to the box. So now we have entanglement with this box. So the cool thing is that there is a procedure called entanglement swapping with which we can glue this entanglement together and create entanglement over the entire distance. So such a box is called a quantum repeater, and we can use it to make entanglement over long distances. So there's a nice feature of quantum that if we have entanglement, we can now send a data qubit by teleporting it across. So I take my yellow data qubit and I teleport it to the other side. So this way we can send qubits over long distances. So we are actually actively working on this box, the quantum repeater. And by 2020 we want to have the first demonstration network in the Netherlands that showcases this box, the quantum repeater. It might become the first quantum internet that actually connects small quantum computers, small quantum processors, in such a way that we can send qubits from any of these quantum computers to another. We can make entanglement between any of these cities.
The basic idea with teleportation is to move a quantum state from one place to another. So when we're talking about teleporting something, we're not talking about physically taking this camera or this table or something and having it reappear in a different place. We're just moving the information that represents it from one place to another in the quantum context. So what is it? We got Alice and Bob. Alice has a qubit, a data qubit, so we'll label it D. And the idea is that Alice wants to take that quantum information and send it from where she is over to where Bob is. So how are we going to go about doing that? So we start with a single qubit, which is in some state that we don't know. Maybe it's something we prepared, or maybe it's something that somebody else prepared and gave to us. We don't know what it is. So what happens? Alice has this qubit. She wants to get it to Bob. So what she does is she begins by creating one of these bell pairs. I'm sorry, in this case, somebody else, a third party, is creating this quantum bell pair to two qubits we call A and B. We take those, we distribute them, one to Alice and one to Bob. So Alice now has two qubits, the data qubit that she wants to send to Bob, and this A qubit, which is a generic resource. So this is something that, that the network can make and that is used for doing this teleportation. She takes her qubits and she performs what's called a Bell state measurement, which is a joint operation on the two qubits. It's not the same thing as measuring the two of them independently. But when she does this, she's going to get 2 bits of classical data out of it, in this case is 0 and 1, and she has to send those to Bob, who then takes those values and uses them to apply either a Z gate or an X gate or both to this qubit, and that recreates the state D that Alice started with originally. So it's moving the information from this. And note that even though in this diagram we drew A and B and coming from one place and spreading out, there's not even a requirement at the mathematical level that these be the same kind of physical qubits. So D could, on the left, could be the state of one of the ions in Tracy's laboratory, and D on the right could be the state of one of the superconducting qubits in Yorktown, if we can figure out how to connect those at the physical level. The mathematics supports that. All right, so at some point in the future, then the job of a repeater in the network is first to make entanglement over a physical link with some sort of neighbor. Second, to be able to take that entanglement that it has with individual neighbors along a path and use that to create entanglement between 2 endpoints, so spanning multiple hops. Third, to monitor and manage errors as it goes. And fourth is to participate in the management of the network itself. They are not like classical repeaters. They are not amplifiers. They are nodes that are actually active devices doing a particular set of operations that are used to help us extend entanglement across multiple hops. So, what are these networks good for and not good for? Very briefly, quantum networks are about new capabilities. Some people sort of naively, when they first come in, they hear quantum, they think something fast is going on. They think maybe we'll either be able to violate the speed of light and transmit information faster than the speed of light. It's not the case. And it's also not the case that quantum networks are going to be some pathway to terabit, exabit, yotta-bit per second kinds of networks. That's not what we're trying to do here. We're going to bring in new kinds of capabilities into the networks, improvements in the number of communication rounds for certain distributed protocols, higher precision, scalability of distributed systems, and whatnot. Going a little bit more into the applications themselves, I divide the set of applications that we can do with a quantum internet into three large areas. There's distributed cryptographic functions, sensor networks, and distributed computation. And as it happens, the crypto functions are relatively low bandwidth in terms of their demands on the network. The sensor networks are high to very high bandwidth, and the distributed computation is also high to very high bandwidth. So certainly in the short run, the crypto functions are going to be the thing that's going to be driving adoption. The others are going to take a little bit more time to get there. But let me go through an example with each one of these categories and show you the kinds of things we want to do. This particular one goes back to an internet draft. We never finished getting this, but the idea is to augment IPsec with keys that were generated using a quantum network, using quantum key devices. And this would take a separate dark fiber that runs through some particular infrastructure, and of course the ultimate data communication actually happens over the internet itself. And if we divide this out a little more abstractly, you're going to have two networks. You're going to have the quantum network and the IP network. And over the quantum network, you're making keys. You're making distributed, shared, secret bits whose secrecy is guaranteed. And then they're actually used to encrypt data that's transmitted across the IP network. So that's the basic structure. Is this useful? If you encrypt data today, the data is secure from now until someone factors a number. If they have recorded your encrypted conversation today that's being sent across the network, and then in 10 years this factoring becomes possible, then they can decrypt the conversation you're having today 10 years from now. And ultimately, of course, we want to get to using this as a one-time pad, and theoretically it'll stay secure forever. All right, so that's the crypto use case. Let's talk about distributed computing. There's a concept known as blind computation, which is secure quantum time sharing, give or take. What you get by being able to do this in a distributed fashion and doing this using a quantum internet and this blind computation is it allows us to execute a computation on the server in which the server learns nothing about the client's data, either the input or the output, nor even the computation, except some sort of upper bound on the size of the computation itself. This is, I think, ultimately one of the driving reasons to build a quantum internet, and it's also going to open up a whole lot of interesting applications across a variety of things. But I've actually found that it's going to take very high data rates in order to execute this for large computations, maybe 10 to the 10, somewhere around there. So this is a long-term goal for getting to the point where we actually have a system for connecting complete quantum computers via the internet and building complete distributed systems as we go. The third scenario that I mentioned was sensor network. There are algorithms that have defined for doing high precision clock synchronization, high precision position finding, and in this particular case, there are also algorithms for taking distributed quantum states and using them in astronomical interferometry, which allows you to get higher resolution images than can be done using the existing interferometry that's done between antennas, like the couple of antennas in this picture. So this looks really great too, right? In theory, we can use this for sorts of cyber physical uses and improving different kinds of sensor networks as we go. Sadly, this one's also an even higher bandwidth. This is probably going to take something like 10 to the 11 operations per second or bits per second, entanglements per second in order to do this sort of usefully. Technical demands. Some of these require only the ability to actually measure photons that come at you. So you're sitting at home, you don't necessarily have to have a complete quantum computer at home, but you've got a pipe coming in, you've got a fiber or something coming in, and individual photons are coming out of that fiber. You need the ability to measure those. That's at one end of the technical spectrum. The other end of the technical spectrum runs all the way from really high precision quantum memories and a large scale quantum computer at your node in order to actually execute interesting algorithms over that. And that's sort of a relatively long way away.
Quantum states have to somehow be stored, but storing delicate quantum states for any length of time is hard work, especially if you don't want insanely expensive supercooled devices. Experimentalists have of course come up with a number of ingenious solutions, ranging from storing entangled photon quantum states in a cloud of cesium atoms, a kind of quantum atomic disk drive, or in the spin state of a single electron in a nitrogen atom embedded in a diamond crystal. There are also proposals for removing the need for physical storage altogether, with repeaters that are entirely photonic. These are great because they're much faster than repeaters that have to transfer quantum states between photons and matter particles. So the current state of the art is that entangled quantum states have been transmitted with photons using fiber optics and lasers. Some researchers have even succeeded in bouncing entangled photons off a satellite. These photons can then transfer their entangled states into a variety of matter storage systems, which may eventually serve as repeaters to extend the range and connect a network of these quantum channels. Reliability and speed are not where we need them to be, but the progress is fast. We currently live in the information age, but it's a classical information age. The quantum age is around the corner.